proud that we today have Lou Ballock with us. Lou Ballock is kind of a legend. He is an editor, he is a publisher by heart. He is absolutely great as a speaker who will tell you, to guide you maybe a bit through the spam of the journals in science, through the incredible truth and no truth that we see every day. And he will, as editor also of the editor and publisher of our peer Nano, show you what is information and what is disinformation. Lou, I ask you to take over the word and to speak.
Well, thank you very much for the invitation, first of all, and for the kind words. I'm not sure I deserve every one of them, but I'm trying. That's the best I can do. So let me share my screen and tell you about literature of fake science in publications, and let me start admitting that the word literature, I borrowed it from Beat, that I heard it from him for the first time, but I find it very pointy and compared to the real literature. And the science is in quotation mark, you will find out pretty soon why. So let's start at the very beginning, in which everyday experiences. Our life today is becoming way more and more complex and more connected. Information is gushing out from every hole, overflow, overload. Sometimes it is hard to know what is true. More exactly, truth is relative, but what information is based on facts or data. And that's a very often, very frequent, that's the right word, very frequent phenomenon, the partial knowledge of things, when it became so complex that nobody understands everything, so we need each other. A classic example is the fable of the Indian fable of the blind man and the elephant. Everybody is observing a different part and completely sure that that is the elephant what he is observing. And what we also know, the growing polarization, education and knowledge, the bottom stays wherever you were, that is close to zero at the very beginning, and the top is further and further over the top, so to say. Every day our life is accelerating every day. That it also shows that it appears that short-term interests often dominate long-term ones, and the individual interests dominate group and society interests. Well, it's understandable. Everybody who has to survive today doesn't really care about tomorrow. Politicization of science is a new, not new, but never been this strong as COVID-19 compared with we had to choose with public health or economy or mental health, and these are not easy decisions. And not everybody is happy ever. And also we also see that virtual reality, artificial intelligence now is present in our everyday life. Let me continue and just state that publications are not science. They are yesterday's information and knowledge, organized towards shared on various media, and all this information, what is shared, has a half-life. It's not valid forever. There are things that for a long time have valid, there are others that's just a very short time. The original role of any scientific publication is to improve our knowledge. We collect data based on hypotheses and perform experiments, control data, that is understand the relations between them, that turns them into information, and we put together these pieces of information to generate knowledge, and that's what we should publish in research articles. And the reviews should should collect these different knowledge, different pieces of knowledge, understand the principles and patterns, and transform it into add it to the common knowledge. The main reasons that are responsible for the dilution of scientific publications, in my opinion, this is my personal opinion, there are 4 of them. And I described it in a recent article on the Precision Nanomedicine website. We published it recently. The 4 things: the commercialization of scholarly publishing, the promotion and graduation rules, all information is now electronic, and simply greed. The history of sharing knowledge. First, old-timers, scientists and philosophers, they just talked to their disciplines. The knowledge was not archived, or if it was burnt away. Then handwritten, stored in books. By the way, we still call it manuscripts. You write it with your hand. Then after came phase 3, when articles were printed on paper and stored in libraries. That was a way of more efficient way of communication, and archiving knowledge was easier. However, these large-scale printing required heavy machinery and professional business organizations. So commercial publishing companies were formed so they can sell, then they multiply and sell this knowledge. To prevent mass copying, a copyright law was introduced because you cannot sell somebody else's, and that's where the requirements of originality and novelty comes from, which is still very much alive in the place of reproducibility. Ownership was always, if you remember, always transferred to publishers. Most of them now still transfer your material, so the printed material they can sold. The computer revolution resulted in, as a first phase, in an explosion in publications. This new technology that changed the ways, increased speed, placed economic burden on libraries. There are a huge number of journals. Nowadays there are 30,000 journals, but at that time when this explosion happened, it was like 12,000 journals, and if you put all of them printed, put it in, it would be the height of the Chomolungma. We increase paper consumption and waste, and believe it or not, in 2021, a scientific paper was published in every 7 seconds of every day in a year. That's 4.5 million papers altogether. And for the first time in human history, today we are generating information faster than they could be evaluated by traditional methods. The second major is the promotion and graduation rules set by funders and institutions. We all know that scientists are now evaluated by their research output, that is quote-unquote impact. They must demonstrate their own value by publishing significant and original results in high-value media. Now we talked about what the original requirement comes from. And with a high-value media, what is perceived to be high-value media, the point is that during this transformation, having publication instead of information exchange, and to the human knowledge, to the body of the human knowledge, having publication became an existential issue. Publish or perish, everybody knows this, expression. And the second one, which that's the obsession with the journal impact factor, which a journal and factor after left off is just talking about impact of your articles, which is again false. We talk to each other again, but we should talk to other people as well. It takes a generation to change this, and it's still very much alive, because the journal impact factor was created to evaluate which journals should libraries buy. The most people were reading these journals and cited. The most cited were the most valuable, because they brought not only the professor's name but the institution's name. So the more people read about the institution, the more precious it became. That's how it worked. But the journal impact factor should not be misrepresented ever as impact. Impact on what? And definitely should not be judged individual authors. Article citations, which is all this impact factor calculation based. determine the journal impact factor, but the journal impact factor says nothing about either the paper nor the authors. For example, if we think about it, if we add up all the publications, everybody in this meeting, today's meeting, then calculate the average number of publications and in what journals were they published, what would that number say about any of us? What would they say about the session? Something about the session, maybe. So it's young people and more experience with more citations, but the average is average. Distribution is everything. So then impact. Impact on what? Science, publishers, the profits, the scientists, the departments, your budget. Impact on what? The significance. It is impossible to evaluate the significance or impact of any basic research article or review in advance, only many years after. According to Wang, Song, and Barabashi, that's a very good article in Science from 2013. Takes about 5 years because the citation numbers starting to cross each other. And the reason is the more revolutionary is any findings, then it's definitely not going to be recognized or even denied. Yesterday we had this about dendrimers, which definitely was the case. Everybody knew that it cannot be done until somebody did it. So the third reason, all information is now electronic and remains accessible forever. As the first computer revolution just helped us scientists to create articles, and now the online publishing took over about 2008, 2009, and this again completely new business opportunities. It's very easy. It's not that hard. You don't require those heavy machinery and buy the paper and print it and take it out. It's easy to archive, store, retrieve information, and easy to find what you are looking. Of course, the dark side is that if you are looking for something, you find it and you don't see anything else. So world technical capacity around 2006, 2008, everything is analog or digital format. It's used to be analog and now it's digital format. Science corrects itself, but online publications do not, because you can always access all times. We read the latest publications, the latest issues. Those issues were a year later was put together into books. The books went to the back of the library, to the high shelf. Nobody read it again. Now it's available everywhere, and if you look at it, it's the data has ended 2011, but about 0.2% of articles are detracted. 0.1 out of 1,000 is for fraud and the other for error. Let's say it's 10 times more. It's still just 1%. Electronically live article. There are zombie papers and dead journals. Because a lot of new journals have been started and many of them died. All these papers which were published in these journals, electronic journals now online, these are still available. But an article in a dead journal is not something you would be very proud of. Double submission text manuscripts and according to Retraction Wedge database, about 95,000 articles are still cited after their retraction. Some of them, if you look at that, some of them got more citations after retraction than before. And unfortunately, still there are about 30,000 papers who came out, COVID-19 studies, about 300 of them. Most of them are important beginning. It's just hurried publications that still routinely cited all these, and it's not without any danger. The primary reason, the last one, is greed, fueled by the ease of online publishing. The commonly accepted price for a subscription article about $4,000, and you see that's a recent paper last year about a publication cost is about $600 of a subscription journal, and the profit is about the double. So roughly 35-40%. And all the non-publication costs which are maintaining the business and running the buildings and paying all these employees. Now, what we already knew about these guys, scam emails, bogus meetings, we are all very familiar with that. And we knew about the probably or potential predatory open access publishers, which numbers from 18 rose about 1,000 in 6 years of predatory open access journals. Out of 30,000, it's about 1,000. Of course, there is no sharp border, and those that are involved that debate it very much. But there's also we see in the counterfeit websites. Counterfeit websites that pretend to be a legitimate journal, which was several hundreds. You can read about these and find out them, but there are newest menaces, newest problems. Number one is not importance, but not in the order of importance, but definitely politicization of science and industrialized cheatings, paper mills, and the prep problem. So science is based on validated data, driven by logic, and has a long half-life. Every method which we are using in trying to exclude subjectivity, that is the human element, statistical data range and errors, calculations. However, politics is perception-based and subjective, and it can change anytime, as it originates from human behavior and shifting interests. Just knowing the rules, there are laws, yes, but knowing the rules, just like we know all the rules of chess, but we still cannot tell what will be the outcome in a party of chess. So two people are involved. Economy is definitely profit-driven. Any business that doesn't make profit, it cannot be used. And they're always in conflict by default. One of them dominates, then the other two goes down. At least in the US, it went so bad that the National Academy of Sciences and Academy of Medicine had to come out in an open statement against the politicization of science, overriding of evidence, especially for public health officials. And then there are the new things, fictional institutes. For example, California South University, which has a website, but it doesn't exist. I recommend you to read the Derek Lowe's paper, How Much Published Crap We Will Put Up With in Science, in this year, February. Paper mills. AI is present in our life, and they have people figured that, okay, that is a great opportunity. They can write manuscripts by modern AI power generation techniques and submit them to journals. There is a Russian website, Iranian, of course there is China, and without mentioning governments or countries, about $500 to $1,000 you can be an author in an article that was written by paper mills, and it's very hard to identify. Several thousand of them, and now they are being retracted. Ghostwriting papers on non-existent research in China, according to Wuhan University, it was about $150 million US, 5 times the amount. The preprint problem. Preprints are not peer-reviewed articles, they are unchecked for quality. For every technical solution, there's a good side and there's a bad side. For this one, very quickly, originally you can put it out, and in a short period of time, you can stake out a new area with the preprints, and then the problem is that all preprint servers assign the identification number, and they do not connect to the peer-reviewed version, if ever goes to peer review. So you cannot very hard to find a final record. There is no standard way to retract preprints, even if they prove to be wrong. And they've got the same number of citations, or even more citation and more citation. And very few post-publication reviews are posted. So what can you do? Let's close with that. First of all, check out the publisher. It's not very well known. I didn't know either myself. The Sherpa website, developing open access institutional repositories, which should, every decent publisher should be present in there. Select very carefully where you publish. Instead of listing a long list of advice, just go to thinkchecksubmit.org. That's a very, very useful place. And my final advice, follow Retraction Watch and retractionwatch.com and read the Scientist magazine. There are two examples, the top retractions of 2021 and Retraction Watch reports.
2 minutes.
Thank you. Because every day the actual what's happening, and there are it's entertaining. It's maddening and entertaining at the same time what you can find. So in summary, scientific knowledge becoming more and more interdisciplinary and complex. Volume of academic and library publishing is rising as opposed to but still very much the commercial publishers own the field. Even though taxpayer funded research should be all accessible for free. So my statement is here that fake science in publications is relatively rare. What is the tendency which is alarming, and we speak about a lot, and it feels much worse than it is really. And don't worry, science will be fine, and that's our goal as well. That we work in the precision nanomedicine, which is the CLINAM's Platinum Open Access Journal, which is a scientist-owned. It's free. We just want to promote out science, open access, and we promote all aspects of nanomedicine. Here you find, and just like on the CLINAM page, you find a brief 2.5-minute video that describes where are we, what are we, and why are we doing this. Thank you very much for your attention. Any questions? I'd be happy to.
Thank you very much for this talk. There were no written questions. Do any one of you want to have a question to Lou Balog?
Hi, may I speak up? Good morning.
Good morning.
Absolutely. Hi, Dan.
Hi, good morning. Thank you very much for this presentation. Yes, it's a very important problem that we need to address, the problems that we have in publishing. So I was just wondering what your opinion is about the actual peer review process. I've heard many arguments about whether we should publish the names of the peer reviewers to hold them accountable or keep it anonymous to protect them against negative comments. So what is your opinion?
Okay, my opinion is that let me recall something. From my high school years, we had a very fine analytical balances, and there was a written log. So whatever you did, you introduced the balance. So if something goes wrong, then you know who was there. And of course, it never worked, because if you screwed up something, you didn't put your name down. So that's the anecdote. And my view is, just like in democracy, it's not perfect, it's imperfect, but better than anything else. Now, I intentionally didn't mention peer review. The reason is that, again, previously there was enough time to read, and the peer reviews were peer reviewed, similar people. Now, peer reviewers are much less. So professors write, and 2 layers down, much less experienced the review. So that's another problem. What we do at Precision Nanomedicine and some other journals, we have quite a number of expert members of the editorial board. Most of them are cleanup members as well. and they give you advice to submit a manuscript. They give you advice how to make it better, and that's it. We don't invite postdocs and PhD students and just whoever because somebody has time. That doesn't mean it has expertise. If someone has the expertise, you can, in your own area, then you can decide in 5 minutes whether it is a good paper, it's a bad paper, it's something is missing, or something would you like. That's it's not perfect, but there is. I don't know better. Maybe AI gets to that point, but I'm afraid of that because then not only AI will write papers, but AI will read papers. So we have to keep the human element. Thank you.
Thank you.
Anyone has another question? If this is not the case, I would have one question, Lou. Yesterday we had Aaron Chekhanova with us, and he spoke about the incredible prices that people, due to the fact that they need to show their impact in journals, have to pay a lot of money. And he suggested if it would ever be possible, one should boycott the system to change it. And now you have publishing with PR Nano, which is free to access. And how do you see the fact that young scientists have to pay a lot of money because the wheel of the impact to show it, to perform it, is necessary if you want to go up the ladder in academy?
Yeah, that's what I was referring to in my brief talk. That it's first of all, businesses they are just, in my opinion, they're just using the opportunity. The real problem is the pressure was put on the administration, because it's very easy it's an easy way to say, oh, you publish here and there, and then you are better than others, but it's not true. It's not at all true. There was a paper in Nature a couple of years ago that did show that the top 100 cited papers, 2 was published in Nature, 4 in Science, and everything else was so in a much less impact factor journals. So those money they pay because they have to, and if they have a money. If they don't have the money, then they just can't. So that's what it is. Now boycotting, a number of universities like a California system got together and they denied Elsevier, and they ended up with a couple of 3 or 4 years ago, ended up with a contract that lowered the price. So that's business. That's just simply business. That's all it is. So that's why academic and library publishing rising, because we have to get out these papers. Not to mention that it's very different from tenured people and non-tenured people. Tenured people, they don't really. I mean, I have 100 plus publications as a professor. I don't care if it's 101 or 102. There's not much difference. But from a PhD student, or that's a big difference. I've published 3 papers. And many times and many places, definitely in Asia, it's a must. You cannot get tenured unless you publish. So it's and then there are always some people who goes to the extremes and say, okay, the hell with it, I pay $1,000 and that's gonna be published. And many of these journals are fake journals, are indexed. It's so hard to figure it out, but that's the publisher's problem. It's not the student's problem. So boycotting, if so many people would come together, it works, lowering the price, but it will not make it disappear. So the basis we work, we thought that if we can work for free for commercial publishers, we can work for free for ourselves. that's how this our journal started, the precision nanomedicine, and then of course with Clinum support and all these networks, and that's how we stay alive.
Thank you very much for this talk, and thank you very much for coming back into the session afterwards in the debate lounge. I would now like to say that Silke Krol, unfortunately, is ill, and I'm very glad that Mariana Varna will take over now as the chair of the following two sessions, B and C. Thank you, Lou, and maybe you can get an hour of sleep.
Thank you very much, Bea. Hello, everybody. So now we change the field of research. We focused more particularly on brain therapy, and we are happy to invite Niveta Gunaslan. Niveta received her master's degrees in biomedical engineering from University of Illinois in 2018. And in 2021, she started her PhD in chemical and biochemical engineering under Professor Deepanjan at University of Maryland. And her research are focused on developing novel Ka-age nanoprobes for in vivo multiplex detection of brain diseases. So Niveta, you can start, please.
Thank you, Mariana. Hi, everyone, and good morning, good evening, wherever you are, which part of the world. It's pretty late here, but I am extremely happy to be a part of this summit, and I will share my screen now. Okay, so so today's talk, I'm going to be talking about molecular Ka-age nanoprobes for multiplex photon counting imaging of subdural hematoma in human brain tissues. This is a collaborative effort between University of Maryland, Baltimore, University of Maryland School of Medicine, Baltimore County, the Pond Research Group, and Mars Bioimaging, which is a New Zealand company that came up with a photon counting scanner. So what is subdural hematoma? It is a kind of an intracranial hemorrhage, which is a bleeding in the area between the brain and the skull. It is a bleed under the dura, and because of the location, it can create pressure on your brain, which can impair the function and even be life-threatening if it is not diagnosed or treated on time. Most of the cases start off in the chronic stage when patients usually remain asymptomatic for several weeks or even months. With time, the patients suffer from acute subdural hematoma due to significant bleeding inside the skull that builds pressure against the brain rapidly and requires immediate treatment. The disease has an overall incidence of about 1.7 to 20.6 per 100K persons per year, and it's very common among veterans and elderly persons, and also in other people such as athletes, people who take blood thinners, hemophiliacs, alcoholics, or even babies. It's caused by accidents, falls, any injury during war in the battlefield, or it can also be a natural cause due to aging. The incidence of chronic subdural hematoma is increasing every day, and for up to 20% of the patients, neurological outcomes are deceptively poor, resulting in seizures, heavy breathing problems, loss of consciousness, or even coma. Since the bleeding occurs very slowly in elderly patients, it can go undetected for several weeks or even months. Now, how do we treat these hematomas? Small hematomas can usually be treated using blood thinning medications such as warfarin to reduce the risk of bleeding, but most of the cases involve surgery. Surgical drainage is needed if the blood is localized and it has transitioned from a clot to a liquid consistency. And a lot of the other require craniotomy to be performed to remove larger hematomas. Now, our group realized that there is an unmet clinical need here to prevent subdural hematoma from going undiagnosed or misdiagnosed, which can have serious repercussions such as paralysis or even death if not treated on time. Now, currently, there are several diagnosing imaging modalities for diagnosis. And the most primary imaging modality for subdural hematoma is computer tomography, which is CT, but it comes with a lot of limitations. CT has poor soft tissue contrast, and it has a high case of misdiagnosis due to strong attenuation from beam hardening effects, calcifications in the tissue, or even metal artifacts that may be present in the patients. And also, a lot of the times it can be misdiagnosed. Chronic can be misdiagnosed as acute or otherwise. There is dual energy computer tomography, which is relatively new, and it has higher sensitivity compared to conventional CT. It is capable of material differentiation between iodine, calcium, and hematoma, but also has high radiation exposure, and chance of misdiagnosis is still possible. There is MRI, which is one of the most sensitive screening tools for subdural hematoma, but it is expensive and it has inconveniently long acquisition times, and it's not easily accessible to a lot of patients. It can be claustrophobic, it has its own limitations as well. So right now there is a revolutionary imaging modality, which is the spectral photon counting CT scanner. Recently, the first FDA-approved human spectral CT, the Neotome Alpha, came out, which was by Siemens. It has extremely high sensitivity, low acquisition times, and a lower radiation dosage. So in this work, we are going to be focusing on the photon counting scanner and how we can use nanoprobes, multiple nanoprobes for in vivo multiplexed targeting of subdural hematoma using these photon counting CT scanner. One of the major advantages of PCCT is its material decomposition and artifact correction, and the fact that we can do in vivo multiplexing using multiple KH contrast agents and try and detect multiple biomarkers to improve the accuracy and sensitivity of our diagnosis for SDHP. It provides spatially specific and quantifiable pathological characterization. In this work, we propose to use two different novel KH nanoprobes. One is praseodymium and the other one is hafnium. We chose these because their KH values fall in the ideal energy bins of the photon counting CT scanner. Praseodymium is a 41.9 kilovolt and hafnium is 65.3. It falls in energy bin 2 and energy bin 4 of the CT scanner, which is perfect. So if we can see the material decomposition image over here, that is almost perfect material decomposition between hafnium and praseodymium, and it doesn't really overlap with calcium for the bone either. So it just, we assume that this would be a good pairing for in vivo multiplexing. Our lab has extensive prior data using hafnium nanoparticles. We use them for bone micro damages and also GI tract imaging using PCCT before. It was a recently published work, but we also did do some in vivo studies in animals using praseodymium particles. Praseodymium is a novel contrast probe. It has not been used before. Very little literature on praseodymium. So we are excited to be using this for our work. So what is our approach? Our approach is, so subdural hematoma tissue has angiogenic vessels present in them. Chronic subdural hematoma has angiogenic sprouting vessels, which show alpha V beta 3 integrin expression on these sprouting vessels, which is a biomarker for early stage angiogenesis. And Tie2 receptor is another marker which is present in mature vessels, which helps to detect vessel maturation and disease progression. So we propose to use hafnium nanoparticles targeted with CRGD, cyclic RGD peptide, which will bind to the alpha V beta 3 integrin, which is the biomarker for early stage angiogenesis, and the praseodymium nanoparticles conjugated with the anti-Tie2 or Tie2 antibody, which targets the Tie2 receptor, which will detect the mature vessels present in the tissue. And we can get quantifiable information of how much angiogenesis and how much vessel maturation is present in the patient sample to get an idea of the severity of the disease or where the patient is in terms of the stage of SDHD. So this slide shows the synthesis process for both the nanoparticles, hafnium and praseodymium. Hafnium, these are the TEM images of our particles. Both of them are around 10 to 20 nanometers in size. and hafnium nanoparticle were made from hafnium epoxide, and we coated them with a polymer silane, PEI coating to increase its hydrophilicity, and we conjugated with cyclic RGD. And praseodymium nanoparticles were made from PRCl3, and these form a lipid bilayer. So there are nanoparticles which are present in the lipid bilayer. They form a vesicle. So if you can see the TEM image over here, you can see they form circular structures, and there are nanoparticles which are present inside the lipid bilayer. And outside the bilayer, we have type 2 antibody, which will target the type 2 receptor. These are the data we got for angiogenic specific targeting in human subdural hematoma brain tissue. The University of Maryland School of Medicine has been extremely gracious in providing us with human tissue samples, which were surgically removed from patients. And we made 60 micron thick human tissue slices out of these samples, and we treated them with hafnium nanoparticles, which were conjugated with CRGD. We just wanted to do some ex vivo studies to see if there is actually angiogenic specific binding that happens in these tissues. So we did a no contrast negative controls. The tissues were treated with carbon dots, so we do not see any contrast under CT. Positive contrast negative control, which is basically hafnium particles without any CRGD targeting to see if there is any non-specific binding, and we do see some. But when we do a positive contrast positive control, which is hafnium particles targeted with CRGD, we definitely see a threefold increase in the binding, and we can also see some kind of angiogenic vessels that show up under this binding in CT. We also did some immunohistochemistry to find out, to support our CT data. So we chose 3 different markers: VEGF, which is the angiogenic marker, TIE2 for mature membrane marker, and PCAM for microvasculature marker. And we tried to understand the level of angiogenesis and TIE2 that happens between different patient samples, depending on the amount of staining that happens in these samples. This was also an angiogenesis specific targeting. So we, instead of doing the 60 micron thick slices, we did a larger tissue sample to see how the binding actually looks. This is a 3D representation of how the binding happens inside the tissue. We see that there is angiogenesis spread throughout the tissue. And the right-hand side is a hafnium without CRGD. We do see very little non-specific binding compared to the targeted binding. We also try to quantify the angiogenesis between different patient samples. So based on our histochemistry data, we tried to choose 3 different samples with high, medium, and low VEGF staining, which shows high, medium, and low angiogenesis in the patient samples. And we treated them with our hafnium CRGD nanoparticles to see if there is difference in the binding. And we did clearly see higher binding with higher angiogenesis samples, and then it progressively reduces with lower angiogenesis. Conclusion and next steps. We have successfully synthesized the novel KH nanoparticles and demonstrated that angiogenesis specific targeting is possible in ex vivo human tissue samples, which are surgically removed. But this is a work in progress, so we have next steps. We want to do quantitative multiplex studies in human brain tissues, targeting both the angiogenesis and mature vessels at the same time using the praseodymium nanoparticles in order to improve the accuracy of the diagnosis of the severity of the SDHD in patients. And following this ex vivo studies, we will also be doing in vivo studies to understand the viability of these KH nanoprobes as potential contrast probes for upcoming human photon counting CT systems. This work is currently funded by DoD, Department of Defense. This is the lab, my team in Maryland, and we are not going to be in Maryland anymore. We are moving to Pennsylvania State University in a couple of months. So that's exciting. That's all I have for today. Thank you.
Okay, thank you, Niveta. Do you have some question? If not, we can discuss further during break. So streaming, no question for the moment. Nivet, I have a question for you.
Yeah, sure.
Do you hear me?
Yes, I can hear you.
Okay, great. I'm wondering about the sensibility of detection with this kind of nanoparticle for blood vessel. Do you have an idea on the number of nanoparticle you need to be sure that you detect a vessel?
We did a lot of extensive optimization studies on how much the concentration of our nanoparticles need to be. And then we reached one particular value. Obviously, it requires way more optimization. This is just based off of non-specific versus specific targeting ratios to see which one gives the best value. But we can definitely run higher studies to find out if we can improve the sensitivity.
Okay, very interesting research. Bravo.
Thank you.
So we invite Dr. Daniel Gonzalez Carter. He carried out his PhD studies at the Division of Brain Science in Imperial College London, where he focused on investigating pharmacological strategies to modulate microglial activity to combat neural death in Parkinson's diseases. During his first doctoral position, he studies the interaction of nanomaterials, in particular carbon nanotube and gold and silver nanoparticle, with the brain, focusing on their ability to cross the blood-brain barrier and modulate brain inflammation. After moving to Japan to work at the Innovation Center of Nanomedicine, he started to examine the potential of glucose functionalized polymeric nanomicelle to deliver therapies against Alzheimer's diseases across blood-brain barrier. And now he is developing a novel strategy to target nanoparticle to the brain by exploiting the impermeability of the blood-brain barrier to generate artificial brain targets. So, Daniel, you can start.
Okay, well, first of all, thank you very much for that very kind introduction, and thank you for Cleanum for allowing us this opportunity to present the work that we are doing at the Institute for Bioengineering of Catalonia, IBEC, here in Spain, to, as you say, exploit the impermeability of the blood-brain barrier to generate artificial brain targets. So first of all, why do we need brain targets? And that is because of the presence of the blood-brain barrier. So as we just heard in the previous talk, the blood-brain barrier is a cellular barrier composed of the highly impermeable endothelial cells lining the brain vasculature, which prevents the passage of the vast majority of therapies from the blood into the brain. Therefore, treating neurodegenerative diseases like Parkinson's disease and Alzheimer's disease is actually very difficult. So to be able to help the therapies go into the brain, we can use nanoparticles to load them into the core of the nanoparticle. And to date, the strategies employed to target the nanoparticles to the brain is to attach a targeting ligand to the surface of the nanoparticle, which binds to targets expressed on the cell surface of endothelial cells. In particular, there have been efforts to target transporter proteins such as the glucose transporter GLUT1 and the transferrin receptor transporter. However, all of these strategies have inherent brain specificity limitations, since these proteins are also significantly expressed in the peripheral vasculature. Therefore, there is high off-target nanoparticle uptake into peripheral organs, which obviously decreases the therapeutic efficiency, might increase toxic side effects, and ultimately limits the clinical translation. To exemplify this, these are two papers where the authors successfully delivered nanoparticles to the brain by functionalizing the nanoparticle with ligands targeting either the transferrin receptor or neurotransmitter carriers. But unfortunately, they also saw a high uptake into this, in this case, into the lung, or in this case, into the liver. Therefore, what we are trying to do is move away from using these natural targets to instead exploit the blood-brain barrier impermeability itself to generate artificial brain-specific targets to be able to increase the specificity of nanoparticle delivery. So how are we trying to achieve this? So as we just heard, actually, a key component of the blood-brain barrier impermeability is that brain endothelial cells have a very low rate of endocytosis compared to peripheral endothelial cells. And this was nicely demonstrated by the Chengguagu lab, where they showed that in a mouse model with a genetic modification that leads to a leaky blood-brain barrier, there is a higher uptake of a blood-borne tracer into endocytic vesicles, which transports the tracer from the blood into the brain. And in brain endothelial cells, which have this genetic flaw, the number of endocytic vesicles formed, here you can see them, these invaginations, is more closely associated to the structure seen in peripheral endothelial cells, so in this case, the pancreas. And if this genetic flaw is corrected, the rate of endocytic formation, endocytic pit formation, is reverted back to its low level. So our strategy is to use this characteristic to generate brain-specific targets by firstly labeling the cell surface of the whole vasculature with a molecular label. Then, because of the higher endocytic rate in peripheral endothelial cells compared to the brain endothelial cells, this molecular label is internalized and therefore removed from the surface at a faster rate in the periphery versus the brain, so that after a certain period of time, the only place that the molecular label is displayed is in the brain. Then, by generating nanoparticles functionalized with a linker, which efficiently recognizes this molecular label, we should be able to have no interaction with the peripheral endothelium and only specific delivery into the brain. So we have demonstrated the proof of principle of this strategy in a paper published in PNAS, where we used biotin as a molecular label and polymeric nanoparticles functionalized with avidin as the linker to bind the biotin. And in the core, they have Psi5 so that we can quantify and image the nanoparticles. To be able to attach the biotin in vivo, we used a biotin-related antibody targeting PCAM1. And we chose this because PCAM1 is an interendothelial protein expressed in the whole vasculature, but with higher expression in peripheral organs versus the brain. So it was a good candidate to test our strategy. I will skip through this. So I'll go directly to the in vivo results. So if we inject the antibody, the biotin-related antibody, into the mice, and then wait either 15 minutes, 2 hours, 4 hours, or 8 hours before avidin nanomicelle injection, and then we quantify nanoparticle biodistribution 16 hours later, we see that at the short time interval, the strongest targeting that was seen was to the lung, but we also saw targeting to the brain, heart, and the pancreas. However, as the time interval increases, the targeting to the peripheral tissues steadily decreases, while the targeting to the brain remains fairly constant. Meaning that after an 8-hour time interval, the only targeting that we saw was actually to the brain. And here we can see the biodistribution in the brain in ex vivo fresh tissue by IVIS or fixed tissue by confocal microscopy. And you can see that there's clearly significant increase of nanoparticle accumulation in the brain tissue with the biotin anti-PCAM1 antibody administration and 8 hours afterwards administrating the evident nanoparticles, the nanomycines. So we have shown that this strategy works by molecularly labeling PCAM1. But PCAM1 might not actually be an ideal candidate since, as I say, it is an interendothelial protein. Therefore, the amount of target generation will be limited to the cell-to-cell contact points. Therefore, this will not be optimal to have maximal target generation. And also, it might not have an optimal endocytic profile. Therefore, there might be candidates out there with a better difference in endocytic rate between periphery and the brain. And unfortunately, choosing this candidate is not as simple as targeting overexpressed proteins in the brain vasculature, since we actually tried this strategy by targeting transferrin receptor 1. And conversely, we saw that the molecular label was removed at a faster rate in the brain versus the periphery when we targeted this protein. And this makes sense since transferrin receptor 1 is highly used by the brain endothelial cells to deliver iron into the brain. So it makes sense that its endocytic rate is accelerated. So what we're doing right now is using phage display technology to find proteins which are retained on the brain endothelium with a wider cell surface distribution so that we can have many targets generated on the cell surface, and also have a more pronounced endocytic rate difference between the brain and the periphery so that we can have target generation specifically in the brain in a short time period of time and with a higher specificity. So we are doing this firstly in vitro. So we are using endothelial cells extracted from the lung, the liver, or the brain from rats. And firstly, we wanted to measure the general endocytic rate of these endothelial cells. So to do that, we attached a biotin to all of the cell surface proteins of the 3 cell types. And then after a certain period of time, we measured the amount of biotin available on the cell surface by binding fluorescent avidin. And so you can see that versus the lung and the liver, the rate of internalization of the biotin targets in the brain is 2 or 3 times slower. So what we want to identify are the cell surface proteins responsible for this differential rate. So as I say, we're using phage display technology. So our general panning strategy is to bind the phages to the cell surface of the endothelial cells. And then after a certain period of time to allow for the phages to be internalized into each cell type, we then collect the phages remaining on the cell surface. And then we use these phages to treat the cells again, so to pan again. And after a certain 3 or 4 panning steps, we are hoping to find consensus sequences that allow us to have specific generation of targets on the brain cells. And from these, we will examine which ones have widest cell surface distribution, and obviously which are non-toxic, since we will be asking the peripheral organs to endocytose all of these proteins to be able to selectively generate the artificial targets on the brain endothelial cells. So the panning processes, as I say, are ongoing right now. So hopefully in the next month, we will be in a place to sequence these phages and hopefully be able to share with you interesting consensus sequences. So in conclusions and as future prospects, I hope I've been able to persuade you that we can actually turn the main obstacle of therapy delivery into the brain into an advantage, meaning that we can exploit the impermeability of the blood-brain barrier to selectively retain molecular labels on the surface of brain endothelial cells, which should help us to increase delivery specificity by generating artificial brain targets, specifically on the brain, increase delivery efficiency, since speculatively, perhaps we might be able to generate a higher number of artificial targets versus natural targets available in the cell, in the brain and endothelial cell surface. And importantly, increase the delivery safety, since by using these artificial targets, we will be avoiding to use proteins which have a very important role in maintaining brain homeostasis. So for instance, by delivering iron to the brain, in the case of transferrin receptor, or by delivering glucose to the brain, in the case of the glucose transporter. So with that, I would like to simply thank all of my collaborators. The proof of principle of the strategy was established while I was in Japan. So thank you to my previous boss, Professor Kazunori Kataoka, and to the JSPS for the money. And the work to identify the new proteins is being carried out here in Spain in the lab of Professor Giuseppe Battaglia. So thank you to all my colleagues, and thank you to my funders, the La Caixa Foundation. And thank you to you for listening. Thank you very much.
Thank you very much, Daniel. I don't know if the other participants have some question. If not, I have only a small one question, and after that we can discuss during the break.
Sure.
How you envisage to visualize the in vivo accumulation of nanoparticle?
Yes,
directly?
so I mean, the nanoparticles have Cy5 fluorophore in their core. So simply by fluorescence.
Okay.
If I understood your question correctly.
Okay. Okay. No, it's good. Yes. Yes, it's possible.
So
it's really very interesting.
For the quantification, we homogenize the tissues after thorough perfusion and quantify the fluorescence in a plate reader.
But is ex vivo, but in vivo with a live animal?
Well, I mean, in vivo,
it's far.
we administer the nanoparticle, but then sacrifice the animal, right? And then extract the organs after perfusion.
So now the last presentation is performed by myself. Hello everybody. I'm associate professor at Paris-Saclay University at Institut Galien in Paris, and I'm working now on the development of nanoparticle for cardiac application, and I share with you my presentation. Oops. Just a minute. Okay. So I don't see, okay, this one. Okay, do you see my presentation? Everybody can see my presentation? Okay, thank you. So, hello everybody. First of all, I wish to thanks to Bea for inviting me to do this presentation. And in next few minutes, I will show you the results obtained on a new formulation on cyclosporine A for cardiac application. Pardon. The presentation, the plan of my presentation is divided in a few parts. First of all, I will show you some information about the structure, the origin of cyclosporine A, the mechanism of action, and why cyclosporine A is interesting for cardiac ischemia and reperfusion. And we discuss the first results obtained with this new nanoformulation for cardiac application. Cyclosporine A, pardon. Cyclosporine A was obtained first from Tulipocladium inflatum in 1963, and other species were used to purify it. And now can be synthesized by using chemically, by using unmethylated moieties. As you can see here, it has 7 unmethylated peptide bonds, and it's a cyclic neutral lipophilic endecapeptide. In clinical practice, cyclosporine A is used, and here you can see some example of cyclosporine. We can find it under the name of Neural or Sandimune, which is a self-assembling microemulsion, or Restasis, which is an ophthalmic emulsion, and is used to prevent rejection in organ transplantation. But also for inflammatory diseases like rheumatoid arthritis and psoriasis. And the mechanism of action of this medicine is very well understood now. It inhibits the first mechanism. It inhibits the link to cyclophilin D, and which finally inhibits the complex with the calcineurin. And this will inhibit the dephosphorylation of nuclear factor of activated T cells, and finally no expression of pro-inflammatory cytokine interleukin 2. In the same manner, will inhibits the nuclear factor kappa B, and finally inhibits the expression of pro-inflammatory gene expression. And the third mechanism, which is interested for us, is the fact that cyclophilin cyclosporine A binds to cyclophilin D, which is found on mitochondrial pore and transition on mitochondria, and inhibits thus the MPTP opening. Why this way is interesting for cardiac application? As Natalie explained you, so you see here the mitochondria, and the pore of mitochondria can be are open too rapidly at the reperfusion, and when they are open during the first minutes of reperfusion, the cytochrome C, which is inside the mitochondria, is put outside, and this will sign the death of the cells. So if we block the opening, this rapid opening of MPTP could be benefic for the cells and avoid those the cell death. And with this idea in mind, there are some clinical trials performed, and in 2008, Piot and collaborators showed for the first time that the treatment of patient receiving cyclosporine A at the reperfusion a benefic effect on this patient, and these results were further accepted in a follow-up study. But later, the more mitigated results were obtained. And this mitigated results were, these contradictory results were explained by a whole body biodistribution of cyclosporine A, a low accumulation into diseased area, and a low passage from through intestinal barrier. And to overcome this limitation, nano encapsulation was a strategy, and this strategy was already applied by different teams. Here you can see only a few examples by using polymer. But this strategy shows some limitation, the main limitation being linked to encapsulation of cyclosporine A, the amount of encapsulation. And that's why what we proposed is to link cyclosporine A to a lipid, is here, squalene, because squalene is biocompatible and biodegradable, and we obtain like that bioconjugate squalene cyclosporine, and we precipitate this. This strategy was applied by our team for few active molecules like antibiotics, adenosine, anti-cancer drugs, and antiviral. And it was the subject, work subject of Professor Patrick Ouvreur. And here you can see a brief design of our of the different steps. There are a few steps to obtain this bioconjugate. This strategy of squalenoylation is well mastered by the chemist of our team. So first, cyclosporin A is modified to obtain chloroacetic ester, and this chloroacetic ester will react with trisnorosqualenic acid in order to obtain this bioconjugate. And the bioconjugate will be after that added dropwise under vigorous stirring, and we obtain in a dextrose solution, dextrose 5%. Why dextrose 5%? Because we envisage to inject in vivo. And this suspension is submitted to a rotavap in order to evaporate all ethanol, and we obtain a pure solution of nanoparticle in dextrose. And this nanoparticle were further characterized by using nanosizer for the size, diameter, polydispersity, and zeta potential. And as you can see here, we obtain nanoparticle with a size of 170 nanometers, a good polydispersity index, and a zeta potential around -14. We further characterize this nanoparticle by using another strategy, which is cryogenic transmission electron microscopy. And as you can see here, we obtain a very nice spherical shape with a size around 105 nanometers. After that, we evaluate the stability of this nanoparticle, and we evaluate in two conditions, at room temperature and at 4 degrees, and at 2 and 4 milligram per milliliters. And as you can see here, a nanoparticle kept at 4 degrees, either at 4 or 2 milligram per milliliters, were not stable because they precipitate rapidly. But the nanoparticle kept at room temperature, you see they were stable for a few weeks. So for this active principle, for this nanomedicine, we envisage to keep them at room temperature. Is better. After that, we evaluate the toxicity of the nanoparticle, and to do this, we choose two cell lines. The first one is mouse cardiac endothelial cells, and rat cardiomyoblast. And as you can see here, the toxicity or the overall toxicity is good, but we can see some influence of this nanoparticle on the cell viability. And you can see here in red the results obtained at 4 hours. That's mean after 4 hours of incubation with the nanoparticle, and in green with 24 hours later. And the results were similar on rat cardiomyoblast. And the next question was, do these nanoparticles are inside the cells? And we evaluate the uptake of this nanoparticle. And here you can see the results obtained by using confocal microscopy. To do this, we incubate fluorescent nanoparticle. That means we include during the nanoprecipitation a body P of fluorophore, which is in red, and we analyze at different time points. For cardiomyoblast, we don't see any red fluorescent, any red signal at 2 hours, but we can see this signal after 18 hours. And it was more important at 24 hours. At 60 microgram per milliliters, so a high concentration, we detect more signal, so that means more nanoparticle inside. And this signal was not due to the presence of only body P, since the cells incubated with only body P, with free body P, do not show any signal. And we also applied this strategy for endothelial cardiac cell lines. And as you can see here, the signal was detected as early as 2 hours for both concentration 12 and 60 microgram per milliliters. And we obtained a kind of plateau between 18 and 24 hours. And once again, this fluorescence was linked to the presence of nanoparticles, since the body P, the free body P, do not show any signal. And another question, it was, do this nanoparticle can be protective on cells? And to respond to this question, we plate cell lines. Here is the results for H9C2. We plated for during 24 hours. After that, we rinse and we applied the treatment with nanoparticle, and we change, of course, the medium with a special medium for ischemic condition. And we put the plate under hypoxia during 5 hours at 1% of oxygen, under hypoxia followed by reoxygenation, or reoxygenation for 30 minutes, or reoxygenation for 1 hour. And we analyzed by using lactate dehydrogenase test. When the cells are injured, the LDH is released into the medium and can be detected. And here you can see the results. So when the bar are high, that means there are a high detection of LDH. And when the bar are low, that means there are a low release of LDH into medium. And as you can see here, the cells receiving nanoparticle for 24 hours and undergoing hypoxia show a very low amount of LDH compared to untreated cells and compared to cells receiving free cyclosporine and only squalene, the equivalent of higher concentration, that means 60 microgram per milliliters. And this protective effect was also observed on cells under hypoxia for 5 hours, followed by reoxygenation for 30 minutes. And also we saw this effect, but it was a little bit more mitigated after 60 minutes of reperfusion, of reoxygenation. And for endothelial cells, however, the results were more mitigated, and we try to understand why. However, we can see a little bit more protective effect with this amount, that means 60 microgram per milliliters. So this work is ongoing since we are doing a lot of experiment to understand what's happened with the nanoparticle when they are inside the cells, by which mechanism are uptaked, and how this nanoparticle act when they are inside, how it acts on different organs and especially on mitochondria. So we obtain, in conclusion, we obtain this new type of bioconjugate and nanoparticle, which show a good stability and a good size, because 100, it's a good size. And we observe this protective protection on cardiomyoblast, but on endothelial cells, it was not so strong. And we are working on this field now. Before end, I wish thanks a lot of people working on this project and also the different funding association. And thank you very much for your attention.